now that you bring it up.
Oh, apparently the form I sent you was the wrong form. Here's the corrected one. It's like, do you mix that next week? It's like, oh crap, I completely forgot. I set the reminder, so shouldn't lose it. All right, we've got some reminders. All right, so exam this week.
You didn't say exam next week.
Yeah, exam is this week. So the closed portion of the exam, or not the closed, the application portion of the exam went live early this morning. All right, that is due on Wednesday at 6 p.m. Why 6 p.m.? It's because we technically have class on Wednesday. So the plan is if you have problems knitting it and getting it uploaded, come to class, I will help you get it knitted, get it uploaded. All right? We're not technically doing class on Wednesday. All right? The Blackboard portion of the exam goes live on Wednesday early morning, and that'll have a due date like 11:30 at night on Wednesday. So all day Wednesday is basically when it's going to be open.
Like the lockdown thing?
Yep. No lockdown. It is, I don't give enough time for you to look up every answer. And really, if you've been kind of paying attention to the stats, it should be fairly simple. You shouldn't have to really go through and look up. But I also take the stance that if you have a question, you're unsure, and then you go look it up, oftentimes the act of looking it up to find the answer is what triggers the memory formation. So, kind of the approach that I take. Yeah, so, yeah, no, if you try to look up every single question or every single answer in your notes, you will not get anywhere close to finished. So, there's not enough time to do that. So that'll go live. That'll go live on Wednesday. It is basically multiple choice or multiple answer. So some of you have had multiple answer questions before where you'll notice it's a radio button, which is like the circles where as you pick the circle, it'll change, all right? And then there's some that are check boxes. If there are check boxes, you can select as many answers as you think are appropriate, all right? I scale it so you get credit for the correct answers. If you mark a box that shouldn't have been marked, then you get points deducted. But you can never go below 0 points for that question. All right? It's things like there could be fill in blanks too. Fill in blanks for like rounded. Again, this is kind of like the almost like a final exam for the undergrad stats class, but things like, what are the assumptions? You know, what are some of the definitions? You know, like what is a p-value? Or, you know, here's a definition. You know, what are these are related to a p-value? What's the null hypothesis of an ANOVA? Right? What are the assumptions of ANOVA? Those basic questions, and then like, what type of variable is this? What's the scale of this type of variable? So, all right. I can't tell you how many points there are. Just kind of depends on how many questions. I'm going to base it on probably about 35 to 50 points is probably what that exam will be. So if it's 50 points, 50 questions, then you're looking at maybe like 65 minutes to take it. That'll go live on Wednesday. So again, Wednesday, I'll come to class here at 5 to help anybody knit their documents. If you have issues with knitting, you will upload the PDF version. All right, not the Word, you'll upload the PDF to turn it in on Blackboard.
What?
This is the application part, the RMD file, right? You knit it, it knits to a Word, right? Then you save it as a PDF and upload, right?
Oh, that's not what I did.
Good thing. You need to get in here.
Well, I was just gonna work on some stuff.
Go ahead.
Yeah.
Preferably. I'll have to check. Yeah, typically I say PDF because it holds the formatting. Holds the formatting. And then if I wanted it downloaded, I could. We'll see. I have it set up so it is unlimited at uploads. That if you screwed up, uploaded the wrong file, you could re-upload it. All right. And again, as you're working through that, if you run into an error message, you can't figure that out, please email me. Rather kind of solve the error message, right? So that you can continue with that question than to completely stop and not get that question correct. All right. So this is where we left off. Model simplification. So we are working with more than two variables, or in this case, two variables. But as we increase the complexity of the models, we have to go through this simplification step to figure out what is the best model that describes our data. All right, now how we go about doing our model selection depends on a couple different things. Some of it is how many variables do we actually have? How many independent variables do we actually have? Sometimes the number of variables is so large that we're just going to use our information criteria. Make it simple, right? Sometimes we only have a couple variables, so we could use any of them, and classical tests can work as long as all of our assumptions are met. But if we violate normality and equal variances, then we have to do randomization tests. And as I kind of mentioned, if we need p-values to report, these are our two options. But if we get reviewers, if we get major advisors saying, yeah, this information criterion will work, well then go ahead and use it. All right. In theory, if all of our assumptions are met, then all of our methods will yield the same simplest model. All right. If we violate our assumptions, then randomization tests and information criterion should produce the same simplified model. This one could be different, but again, it's because we violate our assumptions. All right, so with the classical test, we can just use ANOVA. In many cases, if you compare the models using ANOVA, you'll get the exact same p-value as if you did one of these type 2 models and looked at the p-values. Because what you're basically doing is dropping a term to see how does that affect our model. Randomization tests are the long way, basically. We're going to do it ourselves using code, using loops to generate our own null distribution of that test statistic. But again, we have that term in one model, we drop it in that second model to see their effect. And then the information criterion is really looking at how much deviance, or how much, I can't really say variation, but it kind of is how much variation is accounted for based on our variables in the model. And we do get penalized by having all of the variables. So you could say, well, isn't having more variables better because we account for more variation? Yes, but if you're adding 2 or 3 variables and all that it adds is 0.1%, then it makes the model too complex. We always want something simple so that we can verbalize and interpret it easily. All right, so we started off with this ANOVA model comparison, just to kind of demonstrate that when we create a full and a main model and use ANOVA, that F statistic and the p-value is going to be the same p-value that we get from our type 2 model, type 2 sum of squares table. All right, so if we're doing classical tests, we really don't have to do this ANOVA full model and main model. We don't need to do that. We could just look at a type 2 table and look at our F values, or our P values right then and there. So in this example, we have this full model, the interaction term's not significant, we drop it. All right, this interaction term doesn't add any significant information to the table. How do I know that? It's because when we drop it, we didn't lose a significant amount. All right, so this p-value says there's no difference between our full model and the model without that interaction term. And if there's no difference in explanatory power, then let's just drop it. Keep the simpler model. So once we do that, and we keep the simpler model, then we can look at our type 2 table again. And since this is a type 2 table, these p-values represent the situation where this date term is significant after we account for cultivar. Our cultivar variable is significant after we account for date. So we're left with a model now where both of our terms in the model are significant predictors of our vitamin C amounts. All right? And I just kind of demonstrate again, when we do these, the full or the more complex and the simpler model comparison, we get our F statistics, we get our p-values that are the same as from a type 2 sum of squares table. All right? So just kind of demonstrating these two different ways. We arrive at the same conclusion, which is, this is our simplest model. Date and cultivar. Those are the significant predictors. Now, where do we go from here? We don't just stop, because we've got additional analysis to do. All right, so looking at our variables, cultivar is a 2-level factor. And at that, we can just stop. We know cultivar is significant, a significant predictor, and all that we have to do then is look at the individual cultivars to make our interpretation. Cultivar 52, no matter what, always has higher vitamin C levels than cultivar 39. Do we have to go do a post hoc test for that? No, we don't. It's a 2-level factor. We know it's significant, so the effect of cultivar 52 results in a higher vitamin C level than cultivar 39. The difference, or the complexity, comes when we look at date. That is our 3-level factor. So we know date is a significant factor in affecting vitamin C, but we don't know that relationship. All right? Graphically, it looks like day 21 is producing the highest vitamin C levels. Right? It looks like day 20 is producing the lowest levels. But we don't know that. Perhaps day 16 and day 20 have no difference. It's this day 21. So this is now our post hoc test. Now we have to go that next step to say, what's different? What is that effect? So these are 3 factors, or 3 levels. This is a categorical variable. In this case, probably an ordinal variable is what I would call it. All right? And how do we do post hoc tests on ordinal or nominal data? Well, we use a Tukey's post hoc test. Does it work here with the 2-way ANOVA? Of course. All right? So Tukey's HSD AOV of a model is going to run Tukey's post hoc test on. Now, the nice thing is since we're looking at a main effects only model, what Tukey's is going to do is run a Tukey's on both of those terms that are in the model. So it'll run it on date and cultivar. But notice in the cultivar, P adjusts to 0. Right? P adjusts to 0. Well, we know that. That's what it should be. Right? It's a significant predictor. And it's only 2 levels, so we should get a difference. But again, did we need to run post hoc tests here? No, we don't. What's important is this. So what we see is that day 16 and day 20, there's no difference. All right? No difference in those. So going back to this graph, these 2 lines, even though they are separate lines on our graph, our statistical analysis is saying that there's no difference in vitamin C levels between the day 16 planting date and the day 20 planting date. No difference. Our difference is in day 21. Day 21 is different from day 16. Day 21 is different from day 20. So that date effect is entirely driven by day 21. Now we can do this using the GLHT, General Linear Hypothesis Test. All right. and this is kind of how I did it. I gave you the code here. Do we have to do it? No, we're going to get the exact same answer as if we did Tukey HSD AOB of our model. So if you get the same exact answer, I just use this. So our writing. Again, 5 things for writing. Our test, our conclusion, test statistic, degrees of freedom, p-value. All right, those 5 things. So, date and cultivar may influence vitamin C levels in cabbage. Data are normally distributed as evidenced by quantile plots, and variances are equal. There's a Brown-Forsythe test. All right? Interaction effect of data and cultivar was not significant. I reported that ANOVA. Where did I get the F statistic, degrees of freedom, and the p-value? From that type 2 sum of squares table. That was not significant. All right? So, that was removed from our model. The most parsimonious model suggests that both date and cultivar affect the vitamin C levels. Again, where did I get these? From those type 2 tables. That's the F statistic, the degrees of freedom, the p-value. It's all there. All right? So now we've reported on our overall test. Now we go to the post hoc. So we know that they have an effect. Date has an effect. Cultivar has an effect. So specifically, cultivar 52 has a higher vitamin C content than cultivar 39, and a planting date of day 21 is significantly higher than the other 2 planting dates. Notice I reported on Tukey's HSD for those comparisons. So if we then wanted to say, if we are going for the highest vitamin C level in our cabbages, what should we do? Take cultivar 52, use day 21 planting date. That's our prediction. In order to get the highest vitamin C levels, that's what we should be doing. All right? All right, review. The assumptions of a two-way ANOVA, same as a regular ANOVA. We have to check that make sure that the data are random and independent. I'm going to tell you that in the problem. All right, we have to check normality within each combination of groups. So now, instead of doing, let's say, a QQ plot for every date and QQ plot for every cultivar, we have to do every combination. All right, so you can quickly see, as we add 3 or 4 or 5 variables, it quickly becomes like making tens of QQ plots. All right, then we have to do our equal variance assumption. Brown-Forsythe can do it for us. But if we need to do Fligner-Killeen test, we have to make our own combination of levels. Once we've confirmed that our assumptions are met, then we go proceed with model simplification. Start at the full model with all of the interactions and start removing the higher order terms and working backwards. Remember, if we have a significant interaction term, we must include the main effects of those terms. It's a requirement. So we're going to keep simplifying until we find the most parsimonious model, and our most parsimonious model will be those models where all of our terms are significant. All right. If those terms are significant and they have more than 2 levels, the 3 or more, then we're going to have to run some sort of post hoc test. All right, we're going to have to run some sort of post hoc test. Post hoc test that we typically would run would be Tukey HSD. If you're doing something like a control and then 2 treatments and you don't care if the treatments are different, you're only concerned with the control, maybe you use Dunnett's, but for this class it'll just be Tukeys. Now that's if we have only 1 main effect that's significant, that's if we have only 2 main effects significant, that's if we have 3 main effects significant, or 4 main effects, and so forth. If we have any interaction effect, our analysis becomes much more complicated. And we'll show you how to do that. But for now, we're going to work through plaque size. All right, this is our in-class practice problem. Plaque size.csv is posted. This used to be a microbiology lab. Any of you ASU students took it? But they used to go around to several locations, I think in the building or maybe on campus, take a swab and then smear the swab on a plate just to see what type of bacteria we grow on it. All right? So up this data set. Question is, does plaque size differ between bacteria and swab location? So import the data, view a graph, check the assumptions, find the best model, and then interpret it. Interpret your analysis. What are you looking at?
What?
What are you looking at?
You got the data? Wow. Was it over this one? That was definitely beyond this point.
I was thinking that through.
Yeah, wow. What are you saying?
600 observations.
Nothing.
Oh, I should also tell you that the homework key was posted. Hopefully you found it. Yeah, it's wherever the homework was posted. I also posted the key there, so check the key, check your answers. If you have questions, you can ask.
I just got to know if you would, so I said, you have to live in my pen. You couldn't give me the haircut. I can't. Oh, gosh. Yeah, that doesn't look a little worse. What? I mean, I wouldn't call them all normal.
It's the one.
I mean, the one on the end is kind of weird, but also all that stuff that's on the outside is kind of, it's like, I mean,
At the end.
4, 5, 6, 7, 8 points. And 1, 2, 3, 4, 5. I don't know. I mean, that one's kind of, this like specific one, the stairwell stats, kind of weird. There's maybe 1 or 2 more that are questionable. It's normal.
Well, because I think, I'm gonna say that one did. Yeah, you were right. I wanted you were right, I'd rather do it short than that.
Yeah. Even if some of them are completely.
Yeah, the vast majority.
Yeah.
And the ones that look odd, what's their sample size?
What's the big information that you independent variables for the whole test? That just like puts them together.
The combination of them will make unique levels.
simplifying model, do you have to go stepwise, or can you just go anything that's insignificant?
I don't think you can drop location.
It's not best practice to do that. Just because you, yeah, I mean, when you do the type 2 table, the p-values are reflecting accounting for other variables at or below level. So like in our two-way tables, you can probably get away with it and not be harmed by it. But if you had, say, 3 or 4-way ANOVAs and you remove the main effect because it doesn't seem to be significant, well, if it appears in any other interaction term, you can't technically do that. So you kind of have to go stepwise one at a time. So I would do one at a time just to check.
And then if you did that, and you try it again,
Right, you drop
one factor
then. Well, you keep dropping. So technically, with the stepwise, you do one at a time. There's always that possibility that the p-values will change.
I can't.
I don't know if you can drop location. That's my thing.
Yeah, but it's the interaction term certificate. Drop the interaction term first and then check. Because these broken it down, they use dummy coding stuff, so they kind of report on the averages, but we don't know we need this yet. So I can figure none of these are significant, and the interaction terms are not going to be surprised if it's not significant. Just because of how they use, how they arrange those terms. Like they did alphabetical order. If you made, let's say you did like Staphylococcus first, this one first, maybe then you now find a difference. So yeah, so look at it. You already had your model, right? That's the full model. So it says summary, yeah, do your ANOVA. Do you have one? Yeah, that so not significant, so we simplify. Keep doing that until we hit our point where we only have significant terms in our model.
Oh, that was, yeah, it's called the location next. Okay, except you have like double digits. You have once you first one,
Yeah.
That's just an ANOVA.
Yeah.
So that's where
I'm writing it out. I did that
I mean, you can run it and then do what you normally do. That's what you're saying, that's ANOVA.
What is like
Yeah.
in black side?
This would be.
Is he editing?
Are you like curious?
I thought one of the rules of this is like, you can't drop the things that are, like, you can't, like, it's an interaction. You know, it's still an interaction, you know?
Oh, yeah, those are the.
That's my only thing, because like, I mean, I could just run a diameter back here, but that's not hard. I could do that. We all know how to do that. But I feel like it's different. What I miss, undergrad stack, the these class practice problems with
Um,
and the and everything.
Yeah,
Literally, that was so clutch.
pretty good common sense.
So clutch. So yeah, that's where I'm at. What do you
I'm struggling to come up with the PP plus content. Basically, just if you look here,
You have to do a
really?
Yes.
Okay.
So
R1 would be dynamic, right?
no, because you're doing a subset of
Okay.
Okay,
Okay, so it'd be criteria.
One of them, yeah.
Yeah, and R, location.
Yeah, I did it the other way, but I don't know if that. I don't. But it's just combinations.
Yeah.
Yeah, because those are your two main things.
Okay. So then, like,
And then you gotta look, okay, so,
so like, in this one would just be staff.
If it's multiple R squared,
yeah, so there's
counts
three levels.
for number of variables,
Bacteria,
sample size.
5 levels. So bacteria would be the niche, whatever, the staff, and then the location is like 4 tables.
5, 10. You have to do it every.
Every single combination.
Okay.
They're probably. Like, honestly, it's no, either way, really. So, if location is on nice. What is
Oh.
You just. Oh. Like, put it on.
You think it would be more complicated?
Well, I mean, you're going to do that last.
Yeah. The ANOVA is going to be cut.
Yeah.
If you start to figure out what your next are your different sides. Yeah. Pretty much. If you didn't want to have an effect, I guess. But you have to scratch the steps. Location is not significant. Get that key going, so we dropped it. And we just ran a regular ANOVA.
That is how it works.
I was literally like, no way, it's that easy.
Most of all of our notes.
How frequently would it just?
Oh, yeah. Oh, I guess you have to.
Yeah, you run it. You run it up. Yep. Bacteria are different. You make it 15 keep like that.
You ran on your simple one? The one that's on the.
Yeah, I did regular. It's good, right? You might reg. Just regular right now.
Like versus year weather.
I didn't hear any hail, so I didn't really hear what that.
No, it just kind of drizzled.
We got, I think we got a
Wind
wind.
really blowing.
Yeah, no, our wind was crazy. Our wind was crazy that day. What did you get? Plots are spoiled.
No, only gave me location. Oh, you're good. I did, this was both on 4, and on 8, and then once, this once, this. Yeah. But just.
How's it going? Did you get your simplest model?
Yeah.
Okay, so look at your ANOVA table, right?
Hold on. Hold on. So update model plan. And it appeared as bacteria colon development capacity in that. So just highlight those words, copy and paste it.
So which one do we see?
And then for your update, paste it in place of.
You can see
I feel like for this specific one, box font is probably better because location doesn't really have to
We're gonna
play
use
a
the
role.
same thing on the left,
But I
same
bet,
thing on the right.
I think maybe for other ones where
Location.
both independent variables are significant.
There you
maybe
go.
it's
So
more
you
accurate.
dropped your interaction term.
I asked him, he said,
So now you just have to
I bet it's like got some.
Yep, so which
No,
one's
that
not
makes
significant?
more sense, I feel like if you're box font on this one.
Alright, so now we drop that one and relook at our main.
So you have to do it in
Yeah.
the model, right?
Yep.
Do it.
Nope,
Okay, that's where I was having an issue, because I did the bacteria location one, I was like, that's more significant location.
Yeah.
I tried to add the location.
Yep.
Okay.
good restaurant to go to. With that,
I like the grill.
the Angry Cactus. Yeah, my wife doesn't want to go there.
The grill is really good.
Yeah, I like that one. It's a possibility. We're trying some place new.
Like fancy, or just like going out.
Go to a restaurant.
You need someplace new, probably think
Oh yeah, now you can't go to Texas.
Mail Palace, 01.
Yeah, has their food improved? Last several times I've been there, I've been
I've only been there a few times.
not as good as when they opened.
I don't know. When did they open? It was before I went to college here, but I have no experience there. Yeah, okay.
2013, 2012, 2015.
Still high school.
I tried CA first.
You know, I don't know.
Yeah.
For cheap.
How much do they charge?
Yeah, I think it's actually pretty cheap here. Because when you buy a thing of beer, I think it's $4 maybe.
Pitcher?
Small.
Yeah.
That's a pitcher.
Yeah.
I don't know, I can't drink a full pitcher at a time. I'm just gonna go.
Man, there was I was in college, local bar, the pitcher was $5.
$5 for a
$5.
That's pretty good.
There was a bar on like a Thursdays. You paid, I don't know, $5 or $8.
Any cover charge?
Yeah, and then you had to buy a cup. The cup was $5. I know the cup was $5, 32 ounce, but you can bring it back.
And they didn't charge you for
Any
that?
other night. But it was nickel to fill.
So nothing. Drink 25 cents and you're gonna get pretty drunk. 125.
I'm sure they made their money off of all the people that were drinking and said that they go, let's do shots.
Yeah.
They still have those deals in bigger colleges.
Yeah, right?
Yeah. Because at K-State, when we went for ASM, they had like nickel PBRs. Yeah.
I mean, obviously it's not gonna be the best beer, but a nickel beer tastes.
It was
better.
worth it.
Yeah, it just tastes
Yeah.
better, knowing that you only paid a nickel.
A lot of the other
A
stuff.
lot of Coors, yeah.
I don't drink
Bud Light.
I can't drink that crappy beer. Unless I'm already pretty drunk.
Coors Light is the same beer as Keystone.
Changed my mind.
Yeah.
Well, it is.
It's just more expensive.
Yeah.
Although I like the banquet one.
Yeah, the only thing that changes is they change what they're loading into the because it takes almost 8 hours to stop the production line, clean the production line, just to start bottling other beers. So they have beers, 2 different beers. In some cases, I think there's one where it's 3 beers, exact same beer, exact same recipe, just a different package.
So they'll never pay for Coors Light, like you buy.
Yeah, just buy Keystone.
Keystone.
You might know this actually. This is something that I've been trying to figure out for years. So you know how on some cans there's the different colored dots on the bottom? What does that mean? They come in the same case, but it's different colors.
I believe those dots are for the ink levels. So it lets the production team know when they have to swap the ink or reload the ink. I believe that is why they have those.
I've been trying to figure this out since I was like 16.
On Jeopardy or something, I don't know.
They probably came on like a how it's made. Have you ever seen that?
Yeah,
The old
yeah.
Discovery or Science Channel. I think they may have talked about that.
Oh, for sure, yeah, they're bound to have
They
that.
probably done it like once or twice.
You'll see those on other things too. Look at like cereal boxes and stuff. You'll see similar things. I think they are entirely there for people judge which one. Because I mean, if it starts going down, it's like you're gonna lose out cases and stuff.
That makes sense.
All right, you guys ready?
Yeah.
Yeah.
Ready to see how to do
All right, let's go through it. Flat size.
I'm not getting any closer now.
All right, so I imported it,
I'm not gonna figure this out.
I did that for.
imported it, I made an interaction plot just to take a look at it. And I see it, okay, so I did it set up to where flat locations on the x-axis, and then I have different lines for the different bacteria. And I look at this and say, okay, so right now it looks like there is a difference in the bacteria diameters, but I'm unsure about these locations. Is there a difference? So I say, well, what is this graph? This graph doesn't look that great. What if I switch the order? Now things look a little bit better. All right, now we can really see, okay, there's definitely, looks to be some pattern here where there's a difference in diameters between the bacteria, but in terms of the location, it kind of looks like all of our lines are going to be parallel. So right now I'm looking at this and thinking, maybe this interaction is not going to be significant. All right, I'm not going to be surprised if it's not significant. I'm also not going to really be surprised if location is not significant. However, we do have this one location fountain that looks like it might be higher than the rest. So maybe I'll see something, maybe I won't. The only way we'll know is if we actually run this to ANOVA. So we start with our assumptions, normality assumptions. So what I did was I kind of went through, did the levels just so I could see what all the names are. And to make it a little bit better, I did subsets just to make all of these plots bigger. So, down here, go, click on it. So I'm just going to cycle through. These are all the different combinations. Right? Every combination I went through. They're all looking pretty good. You know, definitely differences, sample sizes between these various combinations. This one, maybe some points at the out at the extremes, not too worrisome yet, not too worrisome. Small sample size, again, not worried about it. Looking good. This one, maybe. Now we've got both sides that look like they fall out, but it's not like we have 100 data points in here. All right, and taken collectively, you know, all of the other ones are looking good. If it's just this one, I think we're good. I don't have to worry about it. So, I'm gonna show you again. I used the subset functions. I selected on location in bacteria. Right, we're doing QQ plots on the diameter. So I looked at every single plot. Everything looks good. So the next step is our equal variance assumption. So I did a Brown-Forsyth test. Brown-Forsyth can automatically take out every possible combination. P-value is 0.61. We have equal variance. So it looks like our assumptions are met. Let's run through our 2A ANOVA. So I started with our full model, looked at our ANOVA table, and I look at the interaction term. That's what I look at. P-value 0.7384, no difference. All right, so we're not explaining a significant amount of variation when we include this term. So let's drop it. I just did the mod.main and wrote it out location plus bacteria. But if you wanted to do it as the update function, I could. So Matt did it where we're using the left and the same stuff on the left and the right hand side of the equation. However, I am subtracting this term from my model. All right. So that gives me, this line gives me the exact same model as this second line. All right. Yep.
So how would you type in that update function if you had more than one interaction effect to delete?
You delete one at a time and check the ANOVA table, and you just have to keep doing it over and over and over again.
That's what I was saying.
It becomes tedious.
I thought this model knew what it was.
I didn't.
Can you scroll up?
I just created a new model and I did minus location.
All right. Did you just do location minus location?
No, I did location bacteria, created a new model, and did minus location.
Okay.
On that model that I created.
On mod.main.
Yeah.
Yeah, so you could kind of read it into the same model over and over again, but that kind of poses problems if you have to go back and look at p-values and so forth. So
It's confusing.
yep, it's tedious.
I don't know if you would ever want to do this, but can you delete from the left side of the tilde as well?
Yeah. So if you have, let's say, a multivariate ANOVA where you have more than one dependent variable. So example would be if you are measuring shell morphology. All right. All of those are Y variables. You would have a collection of Y variables on the left-hand side. You might want to drop one or two. Why you might want to do that? Not quite sure, because typically you're analyzing those as a set. Cody can fill you in after he learns how to do it.
We'll get back to some of
Yeah. Probably next year sometime.
that.
All right. So I dropped the term. All right. And note that, yeah, our p-value changed. Our F statistic changed. All right. This is why we kind of have to do things iteratively. Is as we drop terms from the model, it's going to affect our values. Why does it affect our values? The residuals. Look at these, 599. That is our error. That's how much of our error is unexplained. This one is 604. All right. What's the difference? 5.3. So what we've done is taken location bacteria out of our model, and it now gets part of our residuals, out of our error term. That error term, if the sum of squares changes, the mean square error term changes, which changes our F statistic, that signal to noise ratio. So we can't just go through, look at this main model and say, I'm going to remove location bacteria and location all at the same time, because removing this could possibly make location significant. Now here it's not. It's 0.46 is a pretty large p-value. It's unlikely to have a significant change. But what if this location was 0.06? Now you have the possibility that changing that error term now makes location significant. So in our main effects, location is not significant. All right, it does not. Its inclusion does not add any significant amount of information to our model. So we simplify it. We remove it. So now we're left with a model where it is only bacteria. And again, I made the model by writing it out and say, okay, I'm going to make the model only with bacteria. But again, if I wanted to use our update function, I could. I would use the update mod.main, again, period, squiggly period, minus location. Again, it's exactly as it appears in this ANOVA table. And this gives us the same model as this LM function. So now when I make that, you can see that we're left with a model with only one significant term, and that is bacteria. So now what do? Well, bacteria has 3 levels. All right. Now we need to figure out which bacteria are different. For that, we're going to do our Tukey's. So Tukey HST on the AOV of our simplified model. And we get this. So Staphylococcus escherichia, no difference in those diameters, but they're different from Pseudomonas. All right. Location didn't have an effect on diameters. Even though our averages might be slightly different, those averages are not significantly different from each other. The only thing that mattered was our species. So now, how do we go about presenting this? Would I use an interaction plot? Maybe. But a box plot of only our bacteria is sufficient because this is the only effect that we see in our model. And when it comes to writing up papers, writing results and conclusions, or discussion sections, we want to present these tables and figures that relay relay what the data are showing. And in this case, it is diameters differ between the different species of bacteria. Could we use an interaction plot? Yeah, probably. But you compare this, which is simple and clearly shows us that Pseudomonas has a lower diameters than the other two. Or something like this, where it's like, oh man, people are going to look at this, see all the lines, and their heads are going to explode and be like, oh my goodness, what do I need to look at? It's simple. There's no difference in location. The only things that differ is bacteria. That's a simple interpretation, but again, the reader's going to see this graph, or your audience is going to see this graph, and eyeballs pop out of their head.
Could you overlay the interaction plot with barks and whisker plot, or show them both in some way?
Maybe. Interaction plots are good if you have a significant interaction. If you wanted to show that location did not have an effect, I would probably do a box plot or a plot of the mean and standard error associated, and kind of have them side by side and say this is figure 1, A is your bacteria, B is your location plot, and have them side by side. There's no significant interaction. Questions?
Could you scroll up to your chunk above the interaction plot? Because I did my code differently, but I got, looks like the same results.
Code differently?
Yeah, I used the width interaction plot.
Oh, with interaction? Yep, yeah, you can do that.
It's okay, it's the same thing. Okay.
Yep, so with plaque size, right? So we're saying,
Yeah, plaque size,
okay,
interaction
so with
plot.
this data frame, we are going to do an interaction plot. So we tell R that all of these variables are found in plaque size. Something like that, right? Yep. All right. Any questions? And hopefully you're kind of seeing that this could be teased. It's easy to do with a two-way ANOVA, fairly easy to do with a three-way ANOVA. But once you start adding 4 or more variables, this whole stepwise process, this iterative process of removing one variable at a time and checking ANOVA tables can become tedious. It takes a lot of time, right? And it's especially hard when you have two variables where the p-values are, let's say, 0.048 and 0.052. So you drop that 0.052 and then all of a sudden that 0.048 might increase, and now we're kind of at a loss. So how do we handle it? All right, so what we're going to do, we're going to stop here because next up is what happens if our interaction term is significant? How do we do that? So instead of trying to introduce it now and then taking a break, let's pick that up on Monday. All right, we're going to do that interaction. Then you will see we will very quickly progress to more than 3 or more variables, because at that point we'll introduce you to our stepwise AICs.
Is there any tests that have multiple dependent variables?
Multiple independent and multiple dependent variables? Yeah.
Could you run like a similar thing?
Blake probably has one. He's got his independent variable could be fish size, fish sex, and lake. And his dependent variables, you would have a separate variable for each parasite species found. So you become a multivariate analysis. Right?
Yeah, sex and season, and then also daytime resting place selection.
Mm-hmm.
Yeah, burrows above ground.
I read ANOVA and I just laugh at it.
No,
All right.
that's what Cameron's in.
What's that?
That's what Cameron's in.
Yeah. All right. So, yeah, don't forget the application part. With the actual like Blackboard quiz, the exam goes live on Wednesday.
Big toes being protected.
I don't know, 4 o'clock, 4:30.